We are now going to look into interesting problem that we also saw in the case of finite element method, but we are going to use algebraic topological method to solve this problem. And in the case of the finite element method, we have done the problem using a 2D approximation. We have not done a 3D problem, we have done a 2D problem. Whereas in the case of algebraic topology, we have to go to a 3D problem because we need certain parameters which are essentially 3D in nature. I will explain this as we go, but now let's look into the problem itself and then see how this problem is structured, what is the physical dimension, and how this problem is going to be replicated using a MATLAB program that we are going to run. So let's start with the problem. So we had this parallel plate capacitor, which was in the case of the finite element method basically a 2D approximation. You had a top plate, you had a bottom plate, and you said the top potential is 1 volt and the bottom potential is going to be 0 volt. So for us to do this problem in the case of algebraic topology, so this is the FEM problem that we saw, but in order to do it in the algebraic topological method, we need to go to the third dimension. So the third dimension is, let's say this is done in this manner and we are kind of coarsely discretizing this grid. So let's say this is our problem in the case of 2D FEM. So this is a 2D problem, and in the case of ATM, as I said, we essentially need to go to the third dimension because we need certain parameters, and this parameter will be, so if this is just for you to compare, this was infinitely long, but we only took a part of the cross section and we solved it in the FEM method. So this was basically a Laplace equation that we solved with certain boundary conditions that we have enforced. But in the case of algebraic topological method, our discretization is going to be tetrahedral. So each face will have certain number of tetrahedrals, and you can basically see each of this triangle is a side of a tetrahedral. So you can imagine that there will be 4 triangles per face, and there are totally going to be 1, 2, 3, 4, 5, 6. So there are going to be 4 tetrahedrals per face, and there are totally 6 faces per cube. So we are going to have totally 24 tetra per cube. This is going to be a larger number of elements. In the case of the algebraic topological method, our elements are the 3D elements, they are the tetrahedrals. We cannot solve the problem only using 2D approximation like the way we did it in finite element, but we need to go to the third dimension, and the reason will be obvious when we go into the program itself. So remember, in the algebraic topological method we set certain parameters, and those parameters are going to be the A1, A2 and A3. These are all in the primal grid. A1 will be the gradient, A2 will be the curl, and A3 will be the divergence. These are all in the primal grid, and we will have also the dual grid, which will be A1 tilde, A2 tilde, A3 tilde, and these are the gradient, curl and divergence in the dual grid. And what we have done here is we have set two grids. We are going to have two types of variables. One will be the source variables, the other one will be the configuration variables, and the source variables will be on one grid and the configuration variable are going to be on the other grid. So let's look into the code itself and try to understand how this code is structured in order for you to get a good appreciation of algebraic topological method, and we are solving this for a simple problem of parallel plate capacitor. So this code is using unstructured grid and we are generating it directly using MATLAB. We are not going to use any specific solvers for that, and what we are getting is the primal surfaces, primal edge and all these kind of things, and we are using the primal mesh information to generate the dual grid information. So the dual grids are going to be the grids that are going to help us to associate certain parameters, whereas the primal grid will be for other kind of parameters, and those parameters, as I said, will be either a source variable or a configuration variable. So let's look into the structure of three-dimensional problem. We have the points, we have the lines, we have the faces, and we have the tetras. The dual grid of a point is going to be the dual volume, which is going to be a tetra, or any other volume. So in this case, let's say for the sake of simplicity we call this as a tetra, but this could be of any shape, any size or any form. So it will be a n hedron. The dual of the line will be a surface, the dual of a surface will be a line, the dual of the volume will be a point. So the number of dual surfaces is going to be same as the number of lines. So if we say we are going to have n number of nodes, e number of edges, and s number of surfaces, and t number of tetras in the primal case. The dual case will be the number of volumes will be also equal to n number of volumes, dual volumes. So I put a tilde on the top of it. We will have e number of dual surfaces, and we will have s number of dual edges, and we will have t number of dual nodes. So this way, so this is the number of nodes, number of edges, number of surfaces, number of volumes. So this is the primal and this is the dual. So what we are going to have is the dual grid is going to be the place where we are going to keep the source variables, and the primal grid is going to be the place where we are going to keep the configuration variable. In this case, the potential will be in the primal grid, whereas D will be in the dual grid. D is the electric excitation and phi is the electric potential. You also call it as electric displacement. So the dual grid is going to be the place where we will have the source variables and the configuration variables are in the primal grid. So in our case we will be working only with the configuration variable and source variable in the form that we have described here. Switching them will not give you the right results, so you have to be careful that you don't mix between source variable and configuration variable. And we have discussed the way we define source variable and configuration variable during the lecture. So for people who have missed it, please go back to the lecture module on the algebraic topology and get a sense of what we are doing here. So let's go into the code. So the code is going to be a simple program for computing the value of the potential in a parallel plate capacitor. I said simple because if you have followed the logic of algebraic topology, you will understand how we are solving the problem. So basically what we are solving for is the divergence of D is equal to 0, but we are going to make this equation look in a different way. What we are going to do is we keep the divergence out, and remember the divergence of D is in the source variable. So we are going to have a dual there, and what we are going to write D as we are going to write it as epsilon E is equal to 0. So we assume that E is positive definite, so we will have divergence of E equal to 0, and we know that E is itself is a gradient of phi in the case of a static problem. So we can write it as minus gradient of phi, and the minus sign will go away and we will have this equation. So let's look at the code. What we have done here is we have got a variable as A. So basically this is the variable that we are talking about. So this is the divergence dot the gradient. So this is an operator what we are looking at. The operator has two components. The one is acting on phi, and phi is on the primal grid, so it will be written with no tilde, whereas the one that is operating on D, which is this entire term, is going to be on the source variable and it's going to be on the dual grid, so we have a tilde, and this is phi is equal to 0. What we are going to see is we know that the gradient, curl and divergence in the primal grid and dual grid will have the form A1, A2 and A3 as follows. So we can write this particular equation using this logic what we have got. So let me put it this way so you can see it below. We are going to substitute the value for the divergence and gradient using A1, A2 and A3. So the value for divergence in the dual grid is A3 tilde. So I am going to put A3 tilde, and the value for the primal gradient is going to be A1. So I am going to put A1 equal to phi of phi equal to 0. And of course in the coding of the program what we have written as is this is the dual A3, so we have put it as DA3 dot this is primal A1, so PA1 multiplied by the phi is equal to 0. So this value is a value that we are calling as A, and this is an operator, and this A operator is operating on phi to get the value that we are interested in. And let's go into the code itself one by one and see how we are getting there. So we are generating the primal grid using an inbuilt program create PDE, and we are getting the model, and the model itself looks in this form. It's a parallel plate capacitor, but we are having a 3-dimensional case here. So this is the top surface of the top conductor, there is a bottom conductor, and these are the sides, and as you can see there are going to be tetrahedrals everywhere. In our case before, I explained it in a simplified manner in the paper, where you see that each cube will have several number of tetrahedrals. You have an unstructured tetrahedral. When the tetrahedrals are structured, then you will have certain symmetry, like in the case what we have shown here, whereas in the case of an unstructured grid you cannot predict the number of tetrahedrals that are going to sit on one side of the cube, and we have a very fine discretization, so there are more tetrahedrals sitting than a simple case what we shown. And this is the problem geometry that we are going to use for our simulation. So let's see what we do with this model. Once we have the primal grid, we are trying to get the information about its surfaces. We are forming the surfaces first of all and get certain information about it, and we are also getting the information about the primal edges, and we are going inside each of the surfaces to see the connected edges to that surfaces. And while we are running the code, we always keep track of how much percentage of the work has been done. So we say this much amount of work is done when it is 25%, 50%, so on and so forth, because we know the number of tetrahedrals and number of edges and number of surfaces. Now we are looking at the volumes and the connected edges. We are doing that to create the A1, A2 and A3 matrices. If you remember, the way we have to get the A1, A2 and A3 matrices depends on the connectivity, and these are connectivity matrices, and we are connecting each of the surfaces to the volumes. So we see volumes with each surfaces. Once we do that, we are basically ready to generate the primal A1 matrix, which is the matrix from edges to nodes. Similarly, we will do the same thing to generate the dual grid. The dual grid is generated with the information what we have from the primal grid. Once we have that, we basically create the surfaces of each of the volumes, and we see the assumed direction. This is very important because we need to calculate the A3 matrix, and we generate the dual A3 matrix in a manner. Initially we declare it or initialize it as a sparse matrix. This is very important step so as to make the code run faster. And once we have that, we create the connectivity of each of the surfaces and volumes, and we are able to create the dual of the A3 matrix, and we are calculating the element coefficient matrix A as I explained before using this particular formula, and we are applying the boundary conditions. Remember, the boundary conditions are defined. In our case, the top plate is going to be at 1 volt, at the bottom plate is going to be at 0 volt. This is what we are doing. We are knowing the top plate and the bottom plate based on the initial indication of the geometry itself. You can choose a different geometry, these values will change. This is particularly for the geometry that we are using, and we are solving the simultaneous equation. Initially we had AV equal to B, where B is the boundary condition, and we are able to solve for this equation by inverting the A, and we are plotting the potential distribution for that problem. So if you run this particular problem at the path, what we will get is several information that we are interested. So there are two things. One is the grid itself that is being generated. So this is the grid that we are going to generate. Each surface has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, roughly 14 or 15 tetrahedrals, and we are able to get to the point of seeing the result where we are able to simulate the problem for the potential, and what you see is the potential. This is a 3-dimensional problem, and you will see it is still not a very smooth line the way we wanted. Ideally it should be parallel lines. We don't see the parallel lines because the discretization is very coarse. We see that there are some errors. This can be improved if we go into a very fine discretization and get a better result based on that. So let's now go back to the code and reduce the discretization a bit so as to generate smaller tetrahedrals so that our accuracy can be improved. The way to do that is, in the code we have to set the value for h, which is a parameter that we are going to reduce. So let's go back to the code. So now we can reduce the discretization by changing this value here, which is the h min value. So if we set that H min value to be 0.5, we got the discretization which we got now. So let us reduce it to 0.2 and H max is also 0.2. So if you are discretizing this particular problem in the way what we have done now, we have reduced the mesh maximum and minimum edge length. So you see that we have more fine discretization here, and what we see here is the result, and you can compare that with the earlier result. The results are much more finer, and you see that we still see certain changes in the equipotential line. The reason for that is the grid is still not fine. This will change if we go even finer, and we can do that by changing the value of H in the main code. So now we are going to reduce the H min and H max even finer, so as to see what is the impact of the discretization on our problem resolution. So discretizing it finer is going to take us a long time to run the code, but just to see the proof of concept that we are converging, I am doing this. So you have to make a defined choice of what is going to be your discretization. For 0.1 we are already in a very fine discretization, so I am going to run it. So you will see in the main window that we have 16,192 surfaces, 10,097 primal edges, and we are extracting the data for the primal surfaces, edges and volumes, and with that we will go and do the same thing for the dual edges, dual volumes and dual surfaces, and we are extracting the value and we are seeing the result. So what you see are two results. The first one is the result for the potential itself. So before that, maybe it is worth to go and see the problem discretization itself. This is a very fine discretization, and as you can see we have gone from the initial problem of 0.5 as the minimum and maximum discretization. We have now 0.1 as the cell size, the maximum size of the tetrahedral edges is going to be 0.1, and for this fine discretization we are able to get a result which is also much more refined, and this we can see in the result of the potential itself what we have computed. You can see that the potential lines are much more finer than before, the equipotential lines are much more refined than before, and the way we have computed the dual grid and the primal grid is very characteristic to the way a normal problem is solved in the case of algebraic topology. So what I wanted to do is I wanted to use this opportunity also to do the same problem that we have also saw in the case of finite element method, the conical capacitor. So we are going to do the same problem that we saw before in the finite element method, which is a conical capacitor, and we are going to run the same problem using algebraic topology and see the result. This we will do in the next module. We will come back and simulate that problem using algebraic topological method. Thank you.